Hello everyone. So if you remember in the previous topic we have looked at finding surface integral over a vector field, which is also known as flux, right? So now that subtopic on flux has a lot to do with this topic where we will learn about divergence. And I'm going to show you that after learning this subtopic on divergence, you'll find out that if you have or if you know what shape actually contains the surface of the object that you will want to get the surface integral of, divergence theorem might be the better theorem or much easier theorem that you can use. Alright, so let's just first look at, so flux was from the previous topic and it has a lot to do with the topic that we discussed today called divergence theorem. Alright, so basically what's divergence? Divergence is a local measure of source strength, so basically how strong your vector field is. Alright, so say you have a surface S, alright, and then your surface S actually bounds a volume V. Alright, so basically it means that you have a surface of which it actually bounds a certain volume of an object, and if that is the case, the total flux through your surface S can also be found by using the divergence theorem. So if you remember your flux formula from the earlier chapter, in which say you have a vector field of F, you perform a dot product with the n cap, which is your unit normal vector, which gives you F dot n cap ds. What it's saying is that you can also express this in terms of divergence of F dV. Alright, so this is the difference. As you can see, flux as it is, this is from the previous topic, but what is mentioned is that as long as you know the object of the surface, right, the volume that bounds, and if you have the dimension of the object, then you can actually get an easier alternative to find it through this one. Divergence of F, we will see that later. Divergence of F is just basically the partial derivative of it. Alright, partial derivative of F. Alright, of course, when we talk about dV, okay, so let's just revisit some stuff here, because if we're talking about dV, usually if we talk about, let me just scroll this up, if we normally look at Cartesian coordinate, then I have the dx, I have the dy, and I have the dz, right? And say, just talk about some common shapes that we have. Say if we have cylindrical shape, this then becomes a dr, r d phi, dz, right? Which then gives me r dr dz and d phi, right? And what if I have spherical shape? For spherical shape, I have dr, I have r sine theta d phi, I have r d theta. Alright, therefore I'll have r square sine theta dr d phi d theta. So be mindful that we actually have three components each of my cylindrical shape and spherical shape, because this is what we indicate in terms of its volume, all right, for the dV part. So this is just a little bit of recap of what you have learned earlier, but I thought it helps. So let's just look at one example. This is one of the example in your lecture slide. All right, so say that you have a unit cube, all right, and it sits at each of your x, y, and z plane. All right, can just put it as anything. Maybe if this is x, y, this is z, and each of it sits at 0 1 for each. Alright, so which means over here this is 1, over here this is 1, and over here this is 1. Alright, and say you have this unit cube in x, y, z plane. Alright, and what they actually ask you to find is to compute the flux of your vector field F, alright, through the boundary of the cube. Through boundary of the cube. I'm not going to write down the whole question here, as long as you just get a gist of what it is. Alright, and the F is actually given by y square I plus 2xy plus z square j plus 2yz k. Alright, so having learned the previous topic, if we're talking about flux, how would we solve this kind of question? Of course, for one cube, we each have 6 sides of the cube, right? So again, flux is what again? According to your previous flux surface integral across vector field, alright? It's given by F dot n cap ds, isn't it? So basically, if you solve it using the previous topic method, the normal flux formula, you are going to get, let's say I'm picking up this from the top part. So I have my top part of my cube, and my flux will then be directed orthogonal to the surface, right? So what I'm going to do is to get my F dot n cap ds, okay, and get the surface integral of this, and this will lead me to the top surface of my cube. Similarly, for the side part, let's say it's this one here, the side on the right side, which I just shade. So then the flux and the normal vector will actually point to this direction, towards y direction, yeah. And of course, for this one, then the normal vector will point to x direction. So what we do is that we compute each individually up to 6 sides of the cube and sum those all up. Alright, so now I'm going to show you the alternative of what we do when we use divergence theorem. So divergence theorem gives you flux equivalent to the divergence of my F dV. So what it says is that as long as you know the volume that bounds the surface, you can actually just use divergence theorem. Alright, so do try it out yourself on finding the flux using the normal F dot n cap ds, right, the double integral of it, as what we have learned in the previous topic, and then you compare with how we're going to go about this. All right, so how we get the divergence of F is that it's just basically the partial derivative of all. All right, so what it basically means is that first I have got my F. Divergence of F basically means the d over dx of my I plus d over dy of my j plus d over dz of my k. Alright, so if I'm going to write this down, what will I get here? If I perform a partial derivative d over dx of y square here, I basically just get 0, right? Because there's no x component here. And let's move to my j part. If I do a d over dy of this, what will I get? I'll get 2x, alright, plus, this will then just be 0, and then finally d over dz of 2yz. 2yz will then give me 2y, correct? So I'm just performing each derivative of its component and sum those all up. So that gives me the divergence of F, which leads me to 2x plus 2y. Having got this, then we look back at the formula. Alright, so the flux can be obtained by putting the triple integral. Divergence of F gives me 2x plus 2y. Alright, and my dv in this case is a simple cube, So I can just take it according to the Cartesian plane, which is dx, dy, dz. And each is from 0, 1, 0, 1, 0, 1. Right? So if I just continue from here, so let's first get this. And if I am going to integrate this with respect to dx, I will get a 2x squared over 2, right? So this will be cut off, and this will then be a 2xy 1 0 dy dz. All right, this is 0 1 0 1. And from here then, what I will get is I will get a 1 plus 2y, because the lower limit is 0. When I substitute it, it becomes just 0. So yeah, so I'll get this 0 1 0 1 dy dz. Again, I perform integration with respect to y. 1 will give me y, 2y will give me 2y squared over 2. This can be cut off. Alright, limit is from 0 to 1, leaves me with just 1. So this now gives me limit of 0 to 1 of 1 plus 1. When I substitute 0, it becomes 0 again, so nothing much here. So this leads me to 2. Alright, 2 is just a coefficient, I can just put it in front. Then if I integrate dz, I get z, upper limit, lower limit. Oops, sorry about that. So in this case, then what I will get is 2, 1 minus 0, and that's it. Basically, that is my flux through the surface of my cube. Alright, so in this example, you see that this is according to dx, dy, dz. But later on in other questions, when you come across shapes like cylindrical shape or spherical shape, especially a shape on its whole, you'll find out, please try to see if you can use divergence theorem and try it out. You will see that the steps are much simpler actually. Alright.